YouTube. Go live, YouTube.
Myself. That's right.
Den's catching up. LinkedIn is not up. Let's try this again. There we go. We are on LinkedIn also. Okay, guys, sorry. That took a second for it all to catch up, but we are live everywhere, LinkedIn and YouTube. Welcome to This One Time. Andrew, you always do such a good job of explaining it, so I'm going to let you.
Yeah. Thanks, Troy. We're back. Here we are, This One Time, and special episode part 3 of our Building in Public live engineering challenge with Gabby.
Part
3 of 3. This is the
two.
finale, the grand finale. Yeah. My name is Andrew Gillies. I'm the CTO and co-founder at Urban Machine, where we're building robots to reclaim waste lumber from construction and demolition. And so just a quick recap on This One Time. We like to talk about the real engineering challenges in the hardware world that we're facing here. Everyone likes to talk about how hardware is hard, but you don't really get to hear the backstories and what that means on a day-to-day basis. We're here to share that with folks. And this is the finale of a series we've done with Gabby on the hardware team here, where we came up with a challenge in the first part and kind of outlined the problem. And then in episode 2, we talked about what the approach was going to be, and we started actually ordering components. And in episode 3, the finale here, we're going to be talking about the results. We've put it into the robot, we've got some initial data, and we also have the third co-founder, Alex Thiele here, who leads the software efforts, and he's really the customer of this project. Now, Alex has not seen these results yet.
I'm dying to see them.
Yeah.
I really wish I had brought my drum.
Yeah. And so, Alex, you've been waiting a while.
I've been waiting like 2 robot versions for this feature to be stable.
Yeah.
So very excited about this.
So now that I have you on the show, I want to ask, why was this so important to you? Because I'll tell you, the last 2 episodes, as they were sharing all this information with me, repeatedly your name came up. So you definitely were a driving force here.
Very easy. I'm very easy when it comes to beat feedback. Okay, so I think it's worth summarizing what we're doing here, which is we're adding a sensor to our end effector to tell whether it's holding on to something, and basically get us a distance measurement of what it's holding onto. So in this case, nails, and we want to know if it grabbed a nail, if it didn't grab a nail, if it's closed or open, or what's going on. And that's not super trivial because it's a pneumatic end effector. So it's like, from the software perspective, we tell it to close, and then maybe it's closed, maybe it's not, maybe it's holding on to something, maybe it's having a hard time closing, maybe it's grabbing wood, but we don't have very much visibility into that. So right now, when we grab nails, we tell it to go to a location, we tell it to close the end effector and to pull, and we just assume it works every time. But I personally have witnessed it not working a fair number of times. And so that sort of kind of triggered the idea of, well, having more visibility and what's happening in those, half-second increments as things are happening really quickly, and be able to react live would be really helpful. So to summarize, the first reason I'd like it is because we could do things like know if we grabbed a nail, or push further into the wood, or see if we're still digging into the surface of the wood, and if the beak is still closing, or if we completely missed a nail, maybe we can retry that with a different position because the camera told us there was a nail there. So maybe we just kind of should rotate the wrist and try again. But the second reason I initially, this was why we wanted it in the first place, is to get statistics. So we're doing a lot of these nail picking operations with a lot of wood, and it's kind of boring to watch. A lot of the time, people aren't looking at the robot. They're definitely not getting out a clipboard and tallying every time that the robot successfully picks a nail, every time it fails, or getting us an idea of when it's successfully picking, when it's failing more often or not. But with the beak feedback, we suddenly have this ability to know whether every pick grabs something or not. And that gets us a really strong signal as to whether the robot's performing well. Now this is going to completely change how our deployments work, because once we're deployed, the robot's in the field. Engineers have no visibility as to what's going on. And the operators don't have a great idea of how well the performance should be. And now that we've deployed our robot, we actually have a fair idea of how this looks like in practice. And what will happen sometimes is something will go wrong. Maybe there's a kink in the pressure line. That actually happened one time. And for about 4 days, the picking was subpar. The nail picking was subpar. And it was only until an operator kind of mentioned, it feels like it's been worse than usual, that we took a look into it and saw, oh yeah, it's terrible. We need to fix this. But now with this beak sensor feedback, we'll be able to get alerts on the engineering Slack channel 1 hour after a discrepancy has been noticed in the pick performance.
That's exciting.
So, yeah, it ties a lot of things together.
Yeah, absolutely. Okay, so I understand the why, and I understand how Gabby was tasked with this, and why Gabby was tasked with this. Gabby, do you understand that?
Oh yeah,
Did you volunteer yourself?
I was voluntold, but
Voluntold. I have never heard that before. I love that. That is definitely going to get adopted in this house.
Well, should we reveal the results here, and Gabby can talk through them?
Well, tell me what you're about to reveal.
Yeah. So what we're gonna do is we're gonna pick a slide. Gabby put this together this morning. We have the sensor installed, and we put in a few configurations. So beaks fully opened, beaks fully closed, and then grabbing a couple different sizes of nails. And then what we're gonna see is data on the percent of sensor range that we were reading in those various scenarios.
All right.
Yeah.
And how long is this covering? Like, how long have the sensors been?
Oh, how long have we been getting data off of it? Like we got our first data a couple of days ago. Yeah, like 2 days ago, something like that.
Okay.
Yeah.
So brief.
Yeah, this is at the very beginning of
Okay.
this.
Okay, that explains why
All right.
Alex is in the dark.
Here we go.
Zoom in on Alex.
Yeah. Oh, actually, hold on. I'm sharing the wrong. Ah, this is the wrong. Where'd this go? It's this one. Yeah. And why isn't it here now?
It's just doing our screen.
Yeah, that's what I want. Okay.
Oh boy. So I do want to tell a little story. This isn't the first beak sensor that we've had. In fact, our previous deployment had a different implementation of a beak sensor hardware, and one by one, almost within a week, they all broke as the robot started picking nails. So I think that was kind of the big driver for this complete redesign of the beak sensor, was to make it more robust.
Yeah, robust.
Right.
Robustness was the
Yeah.
drink.
It's here to last.
this has survived a couple full evenings of robot operation without all of its guarding. It's pretty good. So, yeah, so far so good.
Yeah, that is actually noteworthy. Obviously, you're not dealing with tiny little delicate things. It has to be able to be handled.
Yeah. So the way that sensor works is it's really simple to install. There are 3 settings on the sensor. One is what your output is, which we're doing an analog output, value between 0 and 4096 or 1 and 4096. And so we set that. The next thing is what your minimum distance to your target is. Our target in this case is a plate that moves up and down as the jaws open and close. And the other one is the maximum distance. So our first set of calibration was fully open, just the jaws like this, and set that to minimum because that's when the plate is closest to the sensor, and then close the jaws and set that as our maximum value. And Alex was finding that that was kind of taking up the full range of the sensor because we were manually closing it, and then when you're pneumatically closing it, it closes a little harder. So it was going a little bit past that range. So this is new to you because today we recalibrated it to just basically move the sensor back a little bit during calibration so that the maximum was happening beyond where the jaws close. So we have some room for wear where this is at like 3/4 of the range of the sensor, and as they wear, it'll go closer to 100, but it won't get to 100, which I think is what you wanted.
Yay!
That's awesome.
Yeah, and the resolution looks great too across the range.
Yeah.
Did,
That was so cool. I need these pictures for myself. I'm seeing like.
is this linear? Does it look to be linear?
I haven't checked that. I think the sensor is supposed to be linear within.
But are the mechanics linear as well?
The mechanics are. That's a good question. I think so.
Well, we could check with this.
We can check.
I'm not about to.
Explain what you're thinking about there. Explain that process.
We're from the software perspective, what we care about is how many millimeters thick is the object that the robot is gripping.
Okay.
And millimeters are famously linear. That is to say that the value from 0 to 1 millimeter is 1 millimeter, and the value from 4 to 5 millimeters is 1 millimeter still. But when you're working with complicated sensor arrangements like this, it's possible that the laser rangefinder that we're using is perfectly linear, and it's reading a distance measurement that's linear, but the movement of this plate might not be linear. Maybe there's a lever or an arc in there that's causing that plate to move different distances for different beak positions.
Okay.
That's not super important. We don't actually have to measure super accurately along the range of the sensor. Like average performance along the range would be helpful. A good average performance, but it's worth knowing and understanding about the sensor.
Yeah.
It is so cool. These pictures are awesome.
Yeah,
I guess at the end of the day, you want to know if it's open, if it's fully closed with nothing in it, or if it's fully closed with something in it.
Well, we've been doing more. Like the logic we have right now is if there's an object, if it, let's say it like grabs something and then pulls back, if it's over 10 millimeters, we assume it grabbed wood, right? And that there was no nail there. If it's between 3 to 10, then it's probably a nail. And we have other checks like, hey, like if it wasn't grabbing anything before the pull and then it grabbed something and then it was measuring something after, that's concerning. We should probably log a warning there for the user that the sensor's acting funky. So all those different cases kind of show up in different ways.
More information, better.
More information, better.
So do you think this was the answer? I mean, the initial question, stage one of our this one-time series here, was what's the answer? Is this sensor doing what you had hoped as a team?
Yeah.
So far, yes. I think we need to see long-term durability. The sensor is also not that cheap, so at some point we're going to redesign the jaws and hopefully better integrate something that we can get for like $20 instead of a few $100s.
Right. That makes sense. And you did talk about how this was something that you had to kind of retrofit. The idea came after the beak had already been designed, and so that was part of the challenge, was to figure out how to get Alex the information that was necessary, but within the design that's already existed.
That's how we were able to get a pretty quick turnaround, is because none of the parts needed any modification. You just kind of added this in.
But it looks like it's native.
Yeah.
Like
Well,
it looks
thank
like
you.
it was this. Once I saw the build, I was like, that feels like the obvious. Like it was built for that. So that's pretty cool, and it's so protected now. And I looked at the old sensors and I got scared because like wires would tear out. That was the common failure case. Is just a nail would hit the sensor and like bend it, or cable, the wires would tear out, and we'd get all kinds of funky readings on our end. And sometimes it would freeze the system. That was fun.
Really
But,
fun.
but no more.
The most fun.
That's awesome. Okay. So right now, do you have it so that it is sensing all four or just one?
We have all four turned on. 3 of them are using the old style sensor, and I think one of them is.
Yeah, because Aiden was building up the new design of Bottom Bird, so while he was building it up, put in these parts. There's some disassembly and reassembly to be done to retrofit it into the other existing birds. So next time we do a maintenance day, we can put those in. And now it's not as high of a risk because we know that this one works, so probably the other ones will be okay as well.
Sure, that makes sense. I mean, and I do think, in line with just our whole mission. I know that you guys, as you're building each new version, you're building for disassembly. You're building so that you can take it apart more easily, and not just for repair, but for next iterations, right? I mean, that's awesome. That's great. Andrew, how are you feeling about all of this?
Pretty great. It's been pretty seamless getting this all in here. Yeah, it looks really well integrated with the design. Yeah, now the fun task of ramping up testing on this and collecting a lot of data off of it, and getting that feature deployed finally. Yeah, because like ultimately that's the goal, is to improve our picking quality and improve the throughput of the machine. And it's going to be a huge step forward in achieving that.
Yeah, absolutely. That's exciting. Awesome. Well, I'm so glad we got to do 3 episodes. I'm wondering what next project we can dig into that will have a multi series episode, or multi series of this one time.
Yeah, we'll cook up something. Yeah.
Probably not. Oh no, there was a beak sensor failure.
Wait, we do have a question. We do have a question from Randall, a design engineer. He's asking, are there any hall sensors?
We looked at using hall sensors. You can buy sensors that actually integrate into the pneumatic cylinder directly, that can basically sense when the piston is in certain positions. For this one, those, if he's talking about the similar sensors we're talking about, those just provide a binary signal. It's either in position or it's not in position. And for this application, we wanted higher fidelity information than that. We didn't want to know just that the jaws were open and closed. We wanted to know the actual displacement, an analog signal coming off of them. So that ruled out that type of sensor for this specific application.
And I'm just seeing if anyone else has any other questions. If not, you guys, this was awesome. I'm really excited that you are, that you guys, I mean, really, if you think about what happened here, you had an idea, you were tasked with the time frame, and here we are already, within just a few weeks. It's up, it's running, it's being tested. That's pretty awesome. So
Yep.
kudos to your team. Good job, you guys.
Gabby, great.
And yeah, Gabby, you get your little spearhead pin for.
That's right, yeah. Engineering strike force. Yeah.
There you go. If you want to find out more information about Urban Machine, please visit our website, urbanmachine.build. We are really excited about this show, and sharing, where we are in the journey of building a wood reclaiming robot. Andrew, you have any closing remarks?
Yeah. Yeah, check us out. Yeah, follow us LinkedIn. Stay tuned for the next episodes. We'll always have fun stuff to talk about. Yeah.
Yeah, and now we're on YouTube Live as well, and making our way on Instagram. All right. Take care, everybody. Have a good weekend.
Thank you.
Bye, Joey.